Well, good morning, dear, and welcome. So today we are going to discuss very interesting topic, and perhaps from today onwards, few lectures will be dedicated for exclusively modeling a humanoid robot, the technique of which differs from um, conventional industrial robots. So, fasten your seatbelt, and I think you'll be excited to learn about the method for solving um, the inverse pose problem. Okay, and pose means position and orientation. Okay, so inverse kinematic solution, inverse kinematics model, inverse pose model, they are same. Okay, now you see, what is the specialty with humanoid robot or cobot? By this time, you know already, right? The specialty is they try to um, aesthetically imitate a human hand or human capability, more specifically dexterity, right? And in doing so, as you have seen in Bexstar, the what we have ended up in getting redundant joints, right? And in case of humanoid robot like now, you have seen that both now and Bexstar, they are not following the Piper's recommendation. So grammatically speaking, unlike industrial robots, almost all of them, okay, follow Piper's recommendation so that, for example, Puma, Kuka, or Scara, so that they can crank out analytical inverse kinematic solution in terms of A10 to function. But this kind of cobot or humanoid robot like Bexstar now, okay, they are their design is such they do not follow Piper's recommendation. That means three consecutive joint axes are intersecting at a point. That is not the case if you see the design of Bexstar or now. So in doing so, they have exposed themselves of not getting, or at least the analytical inverse kinematic solution is not guaranteed. And in fact, you will not be able to get the analytical inverse kinematic solution either for Bexstar robot or now robot unless you make some assumption which strongly constrain the design itself. So here what we'll try to do, we'll try to explain or develop a numerical solution for inverse pose modeling. Okay. So basically, because we have today, what we have enough computational power. Okay. So we can run iterations. Okay. So why not try to get iteratively the solutions of inverse kinematics. Okay. So you are right. More specifically, we will talk about some numerical methods, and the most important one or popular one is Newton-Raphson method. Okay. So basically, let us discuss the Newton-Raphson algorithm for finding solution of a function for which analytical solution does not exist. Okay. So for a general case, let us try to let us consider, okay, a single valued function f of theta. Just I am taking a digression, and although you know, I know very well you know Newton-Raphson method, but I will recapitulate here with a single variable. So f of theta, say, is a function of single variable. Okay, a function of single variable. Okay, single variable, say theta. And the function looks like this, for example. So this is pictorially, we are trying to make you understand Newton-Raphson method geometrically, right? Or you can tell that this is what I am going to discuss is now geometric interpretation of Newton-Raphson algorithm. So if this is my function, what we do, we try to develop an algorithm so that we start from somewhere. Say this is my initial theta value, which is theta 0, and we will try to move in this direction, okay, in this direction, because pictorially, as you see, the solution lies here, right? This is a solution for f theta. Say this is the value for this is the value theta final for which this solution can be obtained. So you'll have to go in this direction. You'll have to run the algorithm so that you can start from anywhere, and you will have to go slowly but steadily in this direction so that you can reach to this point for which the function value f of theta is 0, right? So we are trying to figure out, find our problem is find theta equal to final theta for which f theta equal to 0. Then only I can say that, okay, by definition of solution, then only I can say that theta f is the solution of that function. Okay. So how to move, how to formulate that algorithm? Let us consider a point A let us consider theta initial value equal to theta 0, and at theta 0 the functional value is f theta 0. Okay. So this is functional value, right? F theta 0. So let us try to draw a tangent at this point. So and then let us call it tan psi is equals to, say this is C, this is B, AC divided by BC. So let us define BC. This is okay. So this is actually say delta theta. I am defining delta theta. Okay. So BC equals to delta theta, which is very small value, very small. The smaller you can imagine, smaller than what you can imagine. Okay. So this is the concept of limit. BC equals to delta theta equals to, from here, OC minus OB. Okay. So theta 0, theta 1, theta 2, theta 3. So we are proceeding in this direction step by step. Okay. So what is OC? OC is now theta 0 minus, say, OB, some intermediate value, theta 1. Okay. So delta theta equal to this. Now by definition, I am drawing a tangent at this point. Okay. And by definition, what is this? This is nothing but at the point theta 0, this is the derivative of the function. So that is equals to AC, that is functional value at that point, divided by BC, which is equals to delta theta, which is equals to this, right? Okay, so this gives you delta theta equals to f of theta 0 minus, okay, this is say 2. So from 1 and 2, what you can get? So theta 0 minus theta 1 equals to f of theta 0 divided by f dash. It's first derivative at that point, evaluation of that point, right? So if I take theta 1 in this direction and take theta 1 here and this is there and rewrite, then what you are getting is the following. That tells you theta 1, now I am writing in algorithmic form, equals to, that means earlier theta value, okay, minus f of functional value at that point and first derivative of that function at that point. And this is incidentally is the algorithm we are looking for. Okay, this is called Newton-Raphson algorithm. Numerical. It's a numerical method for solving. So how it will work, you now know, right? So slowly you are moving in this direction. You started from theta 0 and you are moving here until you are so in a more general way, say for n number of steps. So if I start from initial theta n minus f of theta n divided by first derivative of theta n. So this is very general algorithm. It's clear? And as you know, Newton-Raphson algorithm is very famous algorithm because it is very easy to run, but it has, you see, some limitation, of course, that also I need to mention. That in the neighborhood of this point only, okay, wherever you are finding initial guess, in the neighborhood, you will be able to figure out the solution. The solution sometimes, instead of converging, it may diverge. If you are too far away, the nature of the function is such, and you are too far away from the actual solution, so initial guess you could not do in a smart way. So you need to know the nature of the function, which is very difficult though. But this is there is no free lunch, right? So these are the limitation, right? The more you are in the neighborhood of the actual solution, more faster convergence you will get. Okay, so this is Newton-Raphson algorithm in short. Okay, and now let us and this is geometric interpretation, and let us now tell you about mathematically how you can find the it's very simple, using Taylor series of expansion. Okay, using Newton-Raphson method using Taylor series of expansion. Okay, say we have a function again, f theta, single variable function about theta. Okay, and about theta we are trying to find the solution. Theta could be having any value. So I can make a Taylor series of expansion of this function, as you know. If you do not know, you know now. So theta plus delta theta equals to f of theta plus delta theta divided by factorial 1 first derivative of that function f of theta plus delta theta square divided by factorial 2 double derivative of that function at theta plus delta theta cube divided by factorial 3 triple derivative of that function, and it continues. It's a series. Okay, so as large as you want you can make. Okay, more number of terms, more precision will be, right? Now since you see, since in our case, since delta theta is very small, very small, so we can neglect the higher order term, whatever the term, say delta theta square, all the higher order terms from here onwards, right, we can neglect. Okay, so we can neglect any term which is associated with delta theta square, delta theta cube, delta theta 4, all kind of thing, right? To simplify actually, and this will simplify, and we get simplified expression. Okay, simplified expression for plus delta theta, and as you know, right, that so this will be f of theta plus delta theta okay, and as you know we are looking for a solution. Okay, so for, and delta theta is too small, so for solution this has to be equal to 0. So what you are getting is f of theta plus delta theta if first derivative of theta equals to 0. So delta theta equals to minus functional value at that point divided by first derivative, right? Now say we are starting from, say we start from an initial value theta equals to theta naught, and then we also increment say next theta, which is theta 1, equals to my earlier theta plus the small incremental value, right? So if I call it 1 and if I call it 2, so 2 can be rewritten from 1. So from 1, what you are getting is the following. Equals to theta 0 minus f of okay. So this is again the same story. So in a very general way, I am writing now theta n minus f of theta n so this is my Newton-Raphson method algorithm which I got from Taylor series of expansion of a function. And in the neighborhood of theta n, when I am searching for a solution, I can always use this algorithm and get my work done. Okay. So this is very simple, isn't it? Huh? This is from Taylor series of expansion. You have got the same. Okay. From here also, from geometric interpretation, you have got Newton-Raphson algorithm. So now let us practice some problem. Okay. Say example problem. Examples. Number 1. Say I have a function equals to say theta cube minus 2 theta minus 1 is 5. Okay, so this function, right, it is a function. So this function has to be made for equals to 0. Then only you will be able to figure out some theta value which will make this function 0. That means that theta is a solution to this equation where function theta equal to 0. So how to solve it? Okay, so first you see you will keep it aside, n plus 1 assigned with earlier n minus. So this is your right. But to run this algorithm, you need very judiciously initial guess. Otherwise, your theta may not converge. Okay. So, and how to get that? You see, that is the trick. You'll have to say here, it is very easy. Say, put theta equals to say 0, then f of theta is minus 5, negative. Put next put theta equals to 1. So this is, say this is right, theta 1 equals to 1, and then you are getting f of theta 1 equals to 1 minus 2 minus 5 equals to minus 6. Still it is negative. So theta 2 equals to say 2, then equals to 8, 2 cube minus 4 minus 5 equal to minus 1. Okay, so you see, then theta 3 equals to say 3, then we are getting theta 3 equals to 3 cube minus 2 into 3 minus 5, that is equals to 27 minus 11, 16. So you see, this is negative and now this is positive. So what does it mean? You know, that means if you try to just understand, so what is happening? So you have got something like this. So sometimes it was positive and sometimes now it is negative. Okay, so the function was positive for anyway theta value, but so it means that this value for which the function will reach to the 0 lies between these two theta values. So here, so the solution lies between 2 and 3. That's it. So now you will run the algorithm. Okay, so you have got some initial guess. Okay, and even if you have a calculator with some programming facility using answer key and equal to key, you can actually program. You see, first of all, these two things you will have to calculate. So this is already given, okay? Theta cube minus 2 theta minus 5. So you differentiate this function, you are getting minus 2, right? So these are the two things you will have to keep somewhere and say initial value. Now initialize. Now you can initialize, right? Whatever you want, say start from 2.5 equals to theta 0, okay, equals to your theta n, and now run. So for theta equal to 2.5, calculate whatever, and also calculate from these two expression, right? Because you will require this to run this algorithm, and very easily you can run iteration after iteration. When to stop? When there is no appreciable change between theta n plus 1 and theta n, okay? So that means you have reached to the destination, okay? Perhaps, okay, so you started from somewhere, say, so theta n, and then after several iterations, n equals to say 20 or 30 iterations, you have come across here, and there is an appreciable change. Theta n plus 1 equals to theta n. That means, and also you can see the functional value, okay? You can compute always where the function actually changes its value. See, if the function changes its value at some, say, we have a very broad between 2 and 3, and it turns out it may be that between 2.6 and 2.7, right? The function is changing value. So you can again make an initial guess of this, so that fine tune, you should not miss that point, okay? Fine tune and run iteratively the same algorithm with initial guess 2.5, okay? And sometimes we can get a learning rate kind of thing, so that the step for which we will allow this increment to happen will be in our control. So this is called hyperparameter. So assigning hyperparameter like gradient descent algorithm, you can have a control over the Newton-Raphson method, Newton-Raphson algorithm as well, okay? So this is it, and you know that this is very easy, but you please do it. And another problem I am giving, so this is very simple. It can also tackle ugly problem also, right? Say, okay, we can make some, okay. Say equal to 2 theta minus sin theta minus 1. So make it equal to 0, and you can please go ahead and solve, okay? Theta in radian, start from pi by 4 or whatever, okay? You try, same, okay? Only here you have transcendental function, okay? Sin theta is there, which itself is a series. In Taylor series, you can expand and see what sin theta is. So I think this is the recapitulation a little bit, and we will use it. And so now you know that for a single variable, a function with single variable, if it is there, and you can run the Newton-Raphson algorithm to get a solution, okay? To get a solution for the function equal to 0, and it has enormous strength, especially in today's era where computation is very fast. So we will see. So up to this, it is digested, I believe, you will have to do this assignments, okay? Complete this and complete this. Start, where to start, you decide. The way I was checking, and then I decided that we should start from here, and where the function will change its sign, okay? So time to time you will have to calculate this, and so you will have to also do this 2 minus cos theta, right? So this is the derivative of the function. So once you have these two, and you can run Newton Raphson algorithm to find theta, which will be a solution of this function. But as you know, this is there is no free lunch, and it has some limitation. As I told you, that the solution convergence of the solution will depend on initial guess. Very important, initial value. So initial value, whatever you are judiciously selecting, then it will be converging faster. And also, if there are multiple solutions, then you will get only one solution, okay? Because multiple solution means your function may be like this, okay? Say, so many times maybe it is crossing this theta axis, right? So if it is so, and you have started from here, so you will be able to capture only this, okay? Then if you want to guess to find another solution, so you'll have to jump out from here, giving some so this is an empirical method, thumbs rule you'll have to apply, give some so this is your first solution, and you start from here, giving some increment to the theta value, okay, and proceed. You actually proceed and see whether the function is again changing its sign, okay? And if it is so, then again another route is there, and you could find out. But in case of our now coming back to our robotics domain, we'll have to be satisfied, and we'll discuss in my next class that whether this constraint which we are figuring out in these are the inherent constraint. That means the convergence is not guaranteed if wild guess is there, and number two, as you know that inverse kinematics will have multiple solution. Number two, if we are satisfied, or the situation demands that that is the best way, that we will be happy with one solution only, and in those cases with this constraint we'll be able to use Newton-Raphson's algorithm to find the inverse kinematic solution of any humanoid robot. But before doing that, in my next class, I will apply this to our very known, very sophisticated and elegant model, two-link robot manipulator, for which we already have analytical solution. We will try to figure out the numerical solutions using Newton-Raphson method. And then we'll extend it, we'll inject redundancy, and we'll extend our methodology to solve the inverse kinematics problem of Baxter type Cobot or now type humanoid robot, okay? So those will be in the subsequent lectures. Till then, stay safe, and don't forget to make your hand dirty with all these very simple problem, having a calculator or making some program. Please recapitulate your Newton-Raphson algorithm. Have a nice day. Bye-bye.